So welcome back to everyone to the third and last part of Franz Forstneric talk on course on minimal surfaces from a complex analytic viewpoint.
Okay, thank you. We finished last time in the middle of a certain proof, but I have only 2 more slides, in fact, on this proof. So basically what we are proving is that we can always approximate a given conformal minimal immersion on a given compact set in a Riemann surface, which has no holes, so on a Runge set, by a globally defined one. And we saw that actually the main point was what of this proof which we did so far. The main point was that we had a holomorphic map, little f, from that compact set into this null quadric A star, punctured null quadric. And then first, well, we want to approximate it by a map on all of M, which we can do because A star is an Oka manifold, it's a homogeneous manifold. But in addition, we want to have 0 real periods, right? This is important because here when you want to integrate, you want these periods to vanish for the integral to be well defined. And we saw that we can do that by not just approximating the single map, but first creating what we call the spray, which means a family of holomorphic maps whose period values have all nearby values. That's what we call period dominating. After that, we approximate the entire spray, and then we just pick a suitable parameter value for which the periods are again 0. These are the periods on the curves which lie in the given compact set. And this was the non-critical case. What is the problem now, of course, is when you go to M, there will be new curves, and there is no reason that this approximating map will have 0 periods on those new curves. I just arranged that everything is fine on those curves which already lie in K. Okay, so this, the conclusion that we get is only that if you have a pair of domains which have the same homology group, which just means that they are really homotopy equivalent to each other, then there is no problem. There we get what we want. Okay, now we have to explain the critical case, and this is the following. So the basic step in the critical case is when the change of topology is such that you pass one critical point. You have some exhaustion function on your Riemann surface, and there is a critical point which you want to pass, where topology changes. Now, this point can only be, you can of course always choose exhaustion function, which is strongly subharmonic. So there will be no local maxima. So there can be local minima, critical points of index 0, or critical points of index 1. Now, if you have a critical point of index 0, this is not a problem, because what happens there is that the new connected component appears, just a little disk. And you can put any conformal minimal immersion on that disk, and you're done. So that's not a problem. The problem is when you have this situation shown here. So you have a pair of compact domains, and the change of topology is then described. So the critical point now has index 1. So the change of topology is described by attaching. So here you see K, a domain with boundary. And now in the next slide, you see an arc attached to it. There can be many combinatorial cases how exactly this arc is attached, whether, so here I'm showing you one of the standard pictures, but you can deal with all of them in a similar way. So this picture is when genus will increase by 1. When you attach an arc in such a way that its boundary points are attached to 2 different connected components of the boundary of K, to these 2 different Jordan curves. So you add this arc, and next what happens is that you thicken it. So when you thicken it, this is just graphically speaking, it's like adding the pair of pants. Actually, this change of topology is exactly called adding a pair of pants. Okay, so we have to understand how you deal with such case. There can be other cases when you attach this arc with both endpoints to the same connected component of the boundary. And there you don't change the genus, but really technically you do with it in the same way as here. Okay, so how do we do this? Now we know, okay, we represent our conformal minimal immersion in this Weierstrass way, right? With the Weierstrass formula, as we did last time. And now there are two steps. In the first step, I'm going to extend this map F, which is holomorphic on K. I'm going to extend it smoothly across the arc to a map, there should be A star here, from K union E into A star, such that the real part of this integral over the arc is correct. And correct means that it has to be the difference of the values of the already given x at the two endpoints of the arc. Because if you do it this way, well, then it will work out. When you integrate, it will exactly match x where it at the endpoints. Okay, so why is this possible? Well, here I'm using the second property, which I explained last time, namely that the convex hull of this null quadric is all of Cn. So therefore, you can always choose this path, f, such that this integral has any given value. Okay, fine. So this we can do. Now the next step is that you proceed just as before. So I didn't write it out, but what are the steps? First of all, I have to use Mergelian's theorem to say that I can approximate this x, which is now what? It's a conformal minimal immersion on K, but it's just smooth on the arc. But I can actually approximate it by conformal minimal immersion on a neighborhood of K union this arc. That's the first step. And after that, I can apply the non-critical case. Why? Well, because K union E is now the same topology as L. L is just a thickening, okay? So in other words, the non-critical case applies. Of course, I still have to do this same game as I explained last time, that I don't approximate just the single F, but I make a spray and then approximate the spray. And within the spray, I find a good parameter value for which the periods on the previous curves are zero, and these two, and this condition is also kept. Okay, so these are just technicalities, but the idea is pretty clear. And now, once I have these two steps, then the proof finishes in the obvious way, namely you exhaust M, the Riemann surface, and you go by alternately applying these cases which we have considered, namely the non-critical and the critical case. I had other things stated in my theorem, namely there was, let me actually, let me quit this, no. Okay, one thing was I said that we can do interpolation. Interpolation is not a problem by using exactly this technique explained here. Namely, if you want to keep given values at some points, you just have to arrange, when you construct this map little f, you have to arrange that integrals of certain arcs will be correct, so that you'll have this relation. And that means you keep the value when you want to keep it. And this is the same technology. However, okay, then I stated a general position theorem, and this is also more or less the same technique, except that I also have to use transversality arguments. This I'm not going to be explaining because it would be a lot of technicalities to explain. The most additional work is actually required by properness. I also said that not only you can approximate this minimal surface on a small set by minimal surface on the full Riemann surface, but you can make that approximating map to be proper into Rn. Okay, and that properness, of course, requires more work. And there, basically, you go like, more or less like in the complex case, when you try to construct proper complex curves in Cn. a good strategy is to actually, when you attach, for instance, a bump and you want to extend the map to that bump, you first extend one component of the map to make it big there. And then you use the other two components, or perhaps more, as many as you have, to arrange that it's a conformal minimal immersion. That means to arrange all the conditions which you have to. Again, this is a lot of work and I won't be explaining it. And then these techniques, which I have told you about, by the way, this technique really originates in some sense in the work of Gunning and Rossi, Gunning and Simhan from '67, who proved that open Riemann surface immerses into the complex plane. There they also met this problem of fixing the periods, but in their case it was simpler because C star is a simpler thing than this null quadric. The idea is a little bit similar. Okay, so what is the next result which we proved by this technique? The next result is that we can actually describe quite completely the topological structure of the space of all conformal minimal immersions from a given Riemann surface M. So let me denote by CMI, this is abbreviation for conformal minimal immersion, from M to Rn, the space of all such immersions. Okay, so it's a huge space. We want to know something about it. I'm going to fix a holomorphic 1 form on M, and then I can consider the following two maps. So the first map associates to every conformal minimal immersion a holomorphic map into the punctured null quadric. And this is nothing else but this map, that you take your x, you take its differential, the holomorphic differential, divide by theta. This is then the function. This is what we call the Weierstrass data, which I called little f in the previous proof. Okay, so we associate to it its derivative map in some sense, which goes to the punctured null quadric. So this is the first map. The second map is nothing but the inclusion map. Instead of holomorphic maps, you can take continuous maps. Okay, and now I will also consider the subset, a big open subset of this space, which consists of non-flat immersions. Non-flat just means that it does not lie in a plane. Why am I considering this? It's for technical reasons. Flat ones are, first of all, not very interesting. And second of all, they give me technical troubles in the proofs. There seem to be some kind of singularities of this space. In fact, we have shown that if M is sufficiently simple, let's say that if it's a bordered Riemann surface, then this space actually has a structure of a Banach manifold, except for you have to remove the flat surfaces, which seem to be some kind of singular points of that Banach manifold. Okay, so let's now see the theorem. So the first one was that actually this map is a weak homotopy equivalence. And it's a true homotopy equivalence if M has finite topological type. So I'm sure that people know what is a homotopy equivalence, right? This means that the two spaces homotopically look the same. Weak homotopy equivalence means that this map will induce a bijection of connected components, and it will also induce isomorphism on all homotopy groups, say on fundamental groups and then on higher fundamental groups of all homotopy groups of these two spaces. So this, topologically speaking, means that roughly these two spaces are indistinguishable from homotopy theoretic point of view. So this theorem is proved really by combining something which we already know, namely that the second inclusion is a weak homotopy equivalence, and this is just by Oka-Grauert principle, you see, because A star is a complex homogeneous manifold. So this inclusion, so you have, roughly speaking, as many holomorphic maps as continuous maps up to homotopy. But the non-trivial new addition is that this is a homotopy equivalence, this first map. Okay, and the proof is more or less using these techniques which I have been explaining. I'm sorry, I jumped a little bit too far. This was a, I'm sorry, this was because it was a technical problem. I have to go back now. Oh, I have to go back a long way. Let me type here. I'm very sorry about this. Let me type. Where was I? Somewhere here. Okay, the second part of this theorem. So this first part concerns non-flat. As I told you, I don't have such a theorem for the moment. We don't have such a theorem for the whole space because of these singular points. However, for the whole space, we have identified path-connected components. So pi 0 just means path-connected components. And it turns out that the space is connected for n bigger than 3, but for n equal to 3, you have this set. So it's the group Z mod 2, namely the group 0, 1, to the power L, where L is simply the number of generators of the homology group. Why does Z mod 2 appear here? It's because in this dimension, the null quadric in dimension 3, so it's a two-dimensional surface, it has a fundamental group equal to Z mod 2. So basically each loop will be either trivial or it will be this non-trivial element of Z mod 2. And then for each different loop, I mean, you have arbitrary combinations. So that's why this group arises. So we have identified this group. This was a new result too. And furthermore, a further result is that I have been telling you that, that the most special conformal minimal surfaces are those which also have harmonic conjugate, a conjugate surface. So those are the real parts of null immersions, null holomorphic immersions. Those are characterized by the integral, by those periods completely vanishing. And it turns out that the inclusion of this smaller space of real parts of holomorphic null immersions into the space of all conformal minimal immersions is also weak homotopy equivalence. So roughly speaking, all these spaces look the same. Next, the next result, which I'm very happy about also, this was made a few years ago, published in 2019, is about the Gauss map of a minimal surface. So I think I already mentioned the Gauss map, but let's mention it again in general. so let X be a conformal minimal immersion. Then we look at this holomorphic derivative of it, which is a holomorphic 1 form with n components. And this is nowhere vanishing. So it means these components have no common zeros. So I can look at the corresponding Kodaira type holomorphic map to the projective space, where I simply take projectivization of this map. So I take, okay, this is like what you would do in algebraic geometry, right? So you take projectivization of this map. And this is obviously the map that goes into this smooth quadric hypersurface in the projective space, where defined by sum of the squares equal to 0. Okay. And this is a holomorphic map just because all of these components are holomorphic and they have no common zero. So there is no indeterminacy set. And now the result is that, in fact, every map of this kind, which goes into this null quadric, I mean, into this hyperquadric in the projective space. So every holomorphic map is the Gauss map of a conformal minimal immersion. And this, if you take n equal 3 here, then this hyperquadric is a complex curve, and you can easily see, so it's a curve in CP2, and you can easily see that it's a quadratically embedded Riemann surface. So it's a CP1 quadratically embedded into CP2. So in this case, the range of this Gauss map will be just CP1. So this means you can think of such a map as being a rational function, I mean a meromorphic function on X. So in dimension 3, every meromorphic function is the Gauss map of a conformal minimal surface into R3. So I was really very surprised that after 300 years of people studying a Gauss map and, well, maybe 200 years, right? Gauss map and minimal surfaces, that this result finally is new, that everybody is okay. However, okay, this I already mentioned. However, I should add here, and these are some remarks. Okay, first I have idea of proof, just a sketch of proof. There are two steps to do. The first step is rather standard. So first of all, I have this holomorphic map to this quadric. And first I lift it. There is a holomorphic lift to the null quadric. Okay. Why? Because this projection from the null quadric, this projectivization map, is just a holomorphic fiber bundle with fiber C star. So it's a C star bundle over this quadric. And because the fiber is C star, which is Oka, there is a theorem from the Oka theory that that every, first of all, you lift it continuously, which is trivial, no topological abstraction, but then you can lift it holomorphically by the Oka-Grauer principle. Every continuous lift can be changed homotopically to a holomorphic lift. Okay, so this is well known. But the second step is non-trivial. So the second step is what? Is to correct this lifting. So I get this F, but the problem with this F is that periods won't be zero. Of course, if M is the disk, there is no problem because there are no periods. You just integrate it. But if M is multiply connected, then you have to fix periods to be zero. And this you do by a multiplier. So you simply construct a holomorphic function with no zeros such that this will now integrate. So it means that the periods of this form will be zero. And this is quite some work. This is quite some work, but basically the technology is there. It's the one which I explained you. So if you succeed doing that, then of course you see you haven't changed because you simply multiplied by a function and this projection is then the same. So you haven't changed the Gauss map. Okay, so this is the second. And here I have a few comments. Namely, you cannot so the main comment is this one, that these conformal minimal immersions which we prescribe, which we construct, which have prescribed Gauss map, that we cannot choose them to have lots of other properties like completeness or properness. It is impossible in general for the reason that there is it is well known that there is a vast literature on the question how big a set of values in the projective space in CP1 in the Riemann sphere can be omitted by the Gauss map of a complete minimal surface. So without completeness, it's not a problem, but completeness imposes very strong restrictions. So Fujimoto proved in some 30 years ago that the Gauss map of a complete non-flat, meaning not a plane, minimal surface in R3 can omit at most 4 values. And the bound 4 is sharp. And there is a result of min ρ in higher dimensions. How many hyperplanes can such a Gauss map omit? Okay. So this is a very active topic still. This is like, these questions are like, you know, they come back to some kind of hyperbolicity type questions in complex analysis. These questions about the Gauss map. Okay, I'm now getting to the next topic that I'd like to present, and this is a completely different set of techniques which we developed, and this concerns the Calabi-Yau problem for minimal surfaces. And these techniques, I will only show you more or less in pictures what is being done. So first, I'm again recalling what does it mean for the surface to be complete. I already defined this in the first hour. So this means that the induced metric is a complete Riemannian metric on M. So it means that any divergent curve in M, when you map it into Rn, will have infinite Euclidean length in Rn. So such surfaces are of the possibly highest interest in the theory. And quite a lot is known about them. So let me show you here this classical, it's two theorems together, classical theorems about such surfaces. In addition, of course, these theorems concern surfaces which are not only complete, but they also have finite total Gaussian curvature. So the integral of the Gaussian curvature is a finite negative number. It is not minus infinity. Okay, so if you look at such a surface in R3, then first of all, its Gauss map, which is a rational, which is a meromorphic function, will actually have only poles at the ends. So it will extend to a holomorphic map. I'm sorry, I forgot to include one important piece of information. That is that M in such case is, it's because I was editing and I unfortunately left some things out. In such case, M is in fact a compact Riemann surface, which I'm denoting by M bar here, with a few points removed, finitely many points. So it's a finitely punctured compact Riemann surface, and the Gauss map extends to a holomorphic map on the compact surface, to CP1. So it actually is a rational function on M. The total curvature, the total Gaussian curvature then happens to be area of the sphere, well, minus area of the sphere times degree of G. This is a general fact, which again, I should have explained you, but I don't have so much time. I think I mentioned before this formula that the total Gaussian curvature is actually equal to the area of the Gauss map with multiplicities minus the area of the Gauss map. So in case you have such a map, then of course the area will be just the area of CP1, which is 4 pi with a suitable normalization times degree of this map. And also the derivative of X, so the Weierstrass data, has an effective pole of degree at least 2 at every end, which are these finitely many points. So this is the basic information, how these things look like, and you see they're completely algebraic objects. Also, the conclusion is that the map itself is proper, and it approaches a limit tangent plane sublinearly at every end. So these are the sort of pictures which you saw in the first hour. Okay, and because of these results, so the conclusion is that a complete minimal surface of finite total curvature is always proper in Rn. And this led Eugenio Calabi in 65 to pose this conjecture in 65. He thought that there are no complete non-flat minimal surfaces in Rn which would be bounded. He even thought that you cannot even make one bounded coordinate function. Okay, so here, of course, there is one condition which is now omitted. Finite total curvature is omitted. If you add finite total curvature, then this is true, as I just explained you. But this is now the conjecture where still completeness is kept, but finite total curvature is omitted. And he thought that there are no such functions. Actually, he wrote some kind of proof, but it was wrong. It was wrong as it was shown 15 years later by Jorge and Xavier, which exactly disproved it. A much more interesting example was made by Nadirashvili much later in 96. He constructed a bounded, complete, immersed minimal disk in R3, say a complete minimal disk lying in a ball. Okay, but of course the curvature will have to be infinite, right? The total curvature. After that, Xintung Yao, in his review of geometry and analysis, this is the so-called millennial lecture that he gave in 2000, he reviewed many things, and in particular, he touched upon this question of Calabi, and he said that, well, instead of this beautiful result of Nadirashvili, there are still, most questions are still open. So for example, he asked, what are the possible conformal types of such surfaces? So here we have the disk. Do we have other surfaces? What can be said about their boundary behavior? Can the boundary behavior be somewhat nice? Like, can you have Jordan curves, for instance, as the boundary? Then there was well, this motivated people to make string of further results, which I won't all discuss. in particular, okay, so there are two things to be mentioned, that people constructed such examples like Nadirashvili with surfaces which are topologically more complicated than the disk, so of higher genus possibly, and so on, but they could not control the conformal type, except for the disk, due to construction methods. Also, they could not control very well the boundary. In addition then, and in a string of important papers, Kolding and Mininkozzi showed that in fact, Calabi was right if you speak about embedded minimal surfaces of finite topological type. So, so any such thing which is complete has to be proper. And this is in R3 only, not in R4, but in R3. So in R3, the philosophy is that you cannot make the surface complete without going to infinity, okay? In R3, if you want to have it embedded. If you want to just have it immersed with self-intersections, there is no problem, as Nadirashvili showed. So there is a huge difference between embedded and immersed. Further results by Mix, Perez, and Ross in the same spirit, that you can actually have countably many ends. Okay, so let me now explain the new theorems. So the first main new theorem was published in 2015 with a completely different technique of construction method. We showed that if you take a bordered Riemann surface, so a Riemann surface with finitely many Jordan curves as boundary, say at least of smooth Jordan curves, then in fact, if you start with any conformal minimal immersion of the closed surface, so this is compact now, so it will be bounded, we can uniformly approximate it by continuous maps, embeddings if n is at least 5, such that the interior is a complete conformal minimal immersion. And the boundary is a union, disjoint union of Jordan curves. It turns out they have to be non-rectifiable. This is necessary to be non-rectifiable. This thing will have infinite total curvature, and therefore the area will be infinite. And so the boundary has to be unrectifiable, but they can be Jordan curves. Okay, so you see the main advantage in this theorem over everything before is that we can keep the conformal structure intact. The given conformal structure will arise as such a surface. A further theorem published just maybe a few weeks ago in Revista Matematica Iberoamericana is that in fact we can have also the same result with countably many ends. So you take Riemann surface of this kind, take a compact Riemann surface R, and then you remove finitely or countably many geometric disks. But these disks, so this has to be a domain, open set, but the disks can cluster on each other. So there is a Swiss cheese phenomena and so forth. Very complicated phenomena is allowed. And still one can do this. Let me mention that, of course, if the ends were, you cannot have points as the ends, isolated points, because a bounded harmonic function, of course, extends harmonically across the point. So it wouldn't be complete at such an end. So there is still some, you can say this is not the end of the story because there are more complicated Riemann surfaces than this. You cannot take isolated points out, but you could, for instance, take some Cantor set out or something, and about such we don't know. But this is where the theory stands at the moment. Okay. I was going to comment about the difference between our technique and those which were used before. You see, what Jorge Xavier and Nadirashvili developed and what all other people later used is a technique which uses labyrinths, different kind of labyrinths. So here I'm showing you a labyrinth in the disk. What is the purpose of this labyrinth? The labyrinth has connected components, many of them, which kind of intertwine in an interesting way. And the point is that any curve which starts somewhere inside and tries to go to the boundary to avoid the labyrinth has to be very long. Okay, like it goes here and here and here and here. So it's infinitely long, okay? Likewise in this picture. So any curve avoiding most pieces of the labyrinth is infinitely long. And then another important feature of these labyrinths is that they are Runge sets, meaning that they have no bounded connected components, relatively compact connected components. So these are Runge sets, so you can approximate holomorphic functions on them. And this somehow was used to enlarge the intrinsic metric on these connected components, so that, well, if the curve avoids the labyrinth, it will be infinitely long. The image will be infinitely long. I mean, the curve itself and also the image. But if it crosses most of these pieces, then the image will be long because you did something else there. So either way, the image will become infinitely long. But the trouble with their construction method is that at each step, it turns out that a part of the image surface in the space can go too far. So the limit will not be bounded. So they simply cut it away. They simply cut away pieces of the surface to keep it bounded. But what does this mean? That you change the conformal type, and then you get something which is topologically possibly the same, but holomorphically completely different. And so that's not what you want. All right. So the main novelties in our construction method is, which I already outlined, no change of conformal structure. The boundary consists of Jordan curves. Countably many boundary components are allowed. We have actually proved similar results in many other geometries, including for some special minimal surfaces, which are called super minimal in a large class of four-dimensional Einstein manifolds in the so-called self-dual or anti-self-dual Einstein four manifolds. So my conjecture actually is that this kind of result holds in every Riemannian manifold, but how to prove it is beyond the current means. And the method of proof is that we construct a uniformly convergent sequence of sort of spiraling modifications of the surface, which inductively increase the intrinsic metric on the surface and make the limit minimal surface as you like, so complete and uniformly close to the original one. And there are two main tools, which I will explain you in pictures. One is that we expose boundary points of Riemann surface. And the second, the key step is actually the second one. The Riemann-Hilbert, we have developed a Riemann-Hilbert modification, a boundary value problem for minimal surfaces. So this is a classical technique of complex analysis, which has been used extensively. But we developed it in some other geometries, in particular for null curves, minimal surfaces, Legendrian curves. And I think there is a lot of space for further developments of this technique. Is there a question? Maybe not. Okay. So let me continue. What is exposing a boundary point? Exposing a boundary point is the following thing. This will be used to increase the intrinsic distance to one or maybe finitely many boundary points. And this will be useful for the application of the second technique. Okay, so imagine that M, which is my Riemann surface, actually it's a bordered Riemann surface, so it is a domain in a bigger Riemann surface. And in this bigger Riemann surface, which is just this plane, I am attaching at some boundary point P an arc ending somewhere else. So this arc is contained in the complement of M except for being attached nicely here. Okay. So this is in the domain. What do I do in the image? In the image, my X, my conformal minimal immersion is defined on M. It goes to the space, and now I extend it to the arc smoothly in such a way that its image, so here it's written, we extend X smoothly to E such that the image arc is very long, not infinitely, but just finitely, but very long, but it stays close to the image. So it means it's oscillating. You just go back and forth a lot. By Merkelian approximation, I can approximate X by something in the neighborhood of M union the arc. And we do the same thing at finitely many points of M, so that what is left in between, there will be short arcs, which are almost straight somehow, because they are short enough. So, and now the second step of this modification is showed by this red surface. So what am I now doing? I'm now constructing a conformal diffeomorphism from the closure of M to its image, which is some subset of the ambient Riemann surface, such that, okay, if I'm outside of a neighborhood, small neighborhood of P, then I'm close to identity. You see, I have not changed much here. I'm staying pretty close to where I was. However, there is a radical change when I approach P. So P goes to the end of the arc Q, and the small neighborhood of P is being pushed out into this red tube around the arc E. Okay, so I'm kind of growing. Okay, think of the virus, right? The virus is doing exactly this. That's why it's dangerous. It has these tentacles. So I'm actually showing you a kind of a two-dimensional picture of what a virus is doing. It grows tentacles, which are dangerous, but in my case, they're not. They just become helpful. What do I do next? Okay, this construction is not totally trivial. It is trivial, essentially, if M is the disk, because then you can use Riemann mapping theorem with some precision. But if M has some topology, then this is a somewhat non-trivial, but this is a technique which Erland Wald and myself developed back in 2019 for some completely other purpose, which was then used by many people in higher dimensions too, for study of boundary behavior of metrics and so forth. So I'm precomposing X with this phi. So what does this mean? That when I approach P, I will actually go to this very end, but you see X map this arc into some very long arc. So this means that this composition will have a large intrinsic boundary distance to P, because actually you're not going to P, but you're in the new picture going to Q. So I have increased now the intrinsic boundary distance to some finitely many points of the boundary. That's of course not enough, but it's a good step. And now I'm showing you the next technique, the Riemann-Hilbert modification. And this technique does the following. I'm first showing you a very simple two-dimensional picture. So here is the image of my surface in space. And at some boundary point of the image, I attach a minimal disk. And at some other boundary point, I attach another minimal disk. So this G is a minimal disk, which is attached so that 0 goes to X of P. Okay, so I have such a picture. And in fact, I have P varies in an arc. So on each short arc between a pair of exposed points, I choose a continuously varying or smoothly varying family of such disks. And then what I do next? Next, I do this. There is a modification called Y. So it's again a minimal surface, which does the following. It approximates X very closely until you come to these boundary points, P. So this, you see this red line follows the black line until you come to here. When you come to here, you abruptly switch direction and you follow these attached disks. And you want to end up, roughly speaking, on the boundary of these disks. So the approximating surface is now this red one. And what is the effect of this? If you can really do that, the effect is that the boundary distance, intrinsic one, will get increased, because you see, first, if you start inside, you have to get all the way to here. So you have the same boundary distance roughly as X, but then you add this part, which you can sort of prescribe. So you kind of add this, so you enlarge it. Okay, so the point is that, The very basic model case of this deformation in complex analysis is just if you take the unit disk sitting in C2 like this, but then you deform it to such disks that you add in the second component some constant times high power of n. So you have a lot of spiraling in this direction, but you see when n is just slightly less than 1, this will be close to 0. And just at the very end, before you come to the boundary, you do this abrupt change going here, right? Okay, so this is the essence of the technique. I'm showing you now a better two-dimensional or three-dimensional picture. So now you really see an arc. You see this surface, which is really consisting of these disks. These lines are actually round disks, so you should rotate them around somehow. You should, in your picture, make a kind of tube around out of the surface. Okay, and then we do that, right? Okay, so this is the modification. There is a lot of work to actually do this fully. In our book, the technique, the Riemann-Hilbert technique, and its development for this purpose is done in chapter 6, and then the proofs of the theorems which I showed you are done in chapter 7. So I could say that the details fill sort of 1.5 chapter. So there is no way I could really explain it here. One of the really delicate points is to make sure that the surfaces which you construct in this way have no branch points. And after you have this technique, then you just do induction. So here this illustration shows a kind of an inductive step in the construction of a bounded conformal minimal surface as a limit of a sequence of them. So at the jth step, what you do is that you increase the inner radius, intrinsic radius, meaning the distance to the boundary for some number like 1/j, but you make sure that the outer radius, meaning how far in space it goes, will increase only for a square of this number. Because the series diverges, but the squares converge, you'll get a surface which is complete but bounded. This is just an example, 1/j. You can pick any such sequence. And here I have some more pictures. I'm claiming that the extrinsic distance, so the idea is that at boundary points, you in fact push in direction which is tangential to where you are at the time. Why? Because there you can go relatively far horizontally without going further in space very much. Actually, the next picture you see exact calculation. If you push horizontally for this distance, then if the extrinsic radius was in the previous step, this number rj-1, then in the next step, use Pythagoras theorem and you will get this extrinsic radius. So you see that the increase is roughly for 1/j square. So basically, then you argue that, well, what will happen is that the surface will be spiraling a lot, but it will not go extrinsically far very much. So it will stay in a ball in the limit. Okay, to create surfaces with Jordan boundaries, you use the same technique, but you have to apply it more precisely, kind of locally. And I don't have time now for speaking much about that. I'm essentially over at the end of my time, but I would like to show you one final result without the proof, which I think could be of interest to any mathematician, not just to any complex analyst. And you see in a moment why. This is a very recent result from March of this year with Kalai. It is what we call Schwarz-Pick lemma for harmonic maps. So the result is just this one. Let D be the unit disk in C, and Bn be the unit ball in Rn. And n is at least 2. I'm considering a harmonic map from disk to the ball. Harmonic map means that each component is a harmonic function. And I'm assuming that this harmonic map is conformal at one given point, Z. It doesn't have to be conformal everywhere, just at this point. Conformal means angle preserving there, right? Then the size of the differential of f at that point is dominated by this number. First, there is this quantity which looks familiar to you from the usual Schwarz-Pick lemma for holomorphic functions on the disk, right? Okay, so this would be the number if F were a holomorphic map from disk to disk. You would exactly have this number. In addition now, since my map is going to the ball and so forth, and it's conformal just at one point, I have this additional number here. And I will explain the meaning of this number. So here, theta is the angle between the position vector and the tangent plane at that point, is the smallest angle, right? And in fact, let me go to the next slide. This number is in fact nothing else. This number in the denominator is nothing else but the radius of the following affine disk. That you go to the point where the image point, and then you add to this image point this two plane, the image of the differential of f applied to R2. So this is a linear plane. So this is an affine plane. You intersect with a ball, you get an affine disk. And this R is simply the radius of this affine disk. Okay. So this is the inequality, and the next part of the theorem says that this is sharp. Equality holds if and only if F is a conformal diffeomorphism of the disk onto this affine disk. So I have been thinking of the comment which Claudio gave me a few days ago. He said that the only stable minimal surfaces in Rn are the flat ones. I'm telling you here that the extremal minimal surfaces in the ball, minimal disks, let's say in this theorem, minimal disks are flat ones, conformal, I mean these affine disks. Now, why am I saying that this could be of interest to every mathematician? Think of the special case of this theorem when n equals 2. When n equals 2, then this ball is also the 2 disk. Okay, and in that case, of course, radius is equal to 1. So this number is not there, right? Because I just have a unit disk. So what is the theorem saying? It is saying that the 152-year-old Schwarz lemma actually holds for a much bigger class of maps than was thought so far. So the classical Schwarz lemma, which Schwarz discovered, well, one form of this lemma was discovered by Schwarz in 1869. He was trying to give a good sound proof of the Riemann mapping theorem. It was then picked up by Poincaré in 84 and given a more general version. Finally, Pick made his edition in 1915. But we can say that this is a 150-year-old lemma, and is one of the most classical lemmas in complex analysis. All of the hyperbolicity theory comes out of this lemma and its ramifications. Okay, and this lemma is always, I have not found it in, I mean, it's hard to check all the literature because let's be honest, there is something like 1,200 papers in the literature which contain Schwarz-Pick lemma, this term. So, but in any case, you see, it holds for a much bigger class of maps. If you just want to have an estimate at one point, you don't need a map which is holomorphic. Holomorphic map is conformal at each point. You just need a harmonic map, which is conformal at that given point where you want to have the estimate. Okay. So I'm happy about this lemma, I have to say. What is the geometric interpretation of this theorem? It is the following. It says that conformal harmonic maps from the disk to the ball are distance decreasing from the Poincaré metric given by this expression on the disk to the following metric, which is a very classical Cayley-Klein metric on the ball. So the expression is explicit is this one. And this expression probably looks familiar to most of you or all of you. The extremal maps are conformal embeddings on the affine disks, and the differential of any extremal map has at any point has norm 1 when you consider Poincare metric on the disk and this metric in the ball, but it's not an isometry. It turns out that it is not an isometry in differential geometric sense, because in some directions, the derivative is smaller than 1. But if you take the differential in all directions, then it is an isometry in that sense. Okay, the same is true if we replace the disk by any hyperbolic Riemann surface universally covered by the disk, endowed with a Poincare metric, because I just go to the universal covering, which is the disk. And here are some comments about this metric. This metric goes back to, it was first described by Cayley as one of the important models of hyperbolic geometry. It was independently, about 10 years later, described by Beltrami. And then young Felix Klein, who was then in his early 20s, got very interested in this metric and wrote a couple papers. And that's why it bears this name. So the underlying space is the ball, and the geodesics are line segments through a given point, which have endpoints on the boundary sphere. And in fact, the distances on these line segments are kind of defined by cross ratio. And this was then developed by David Hilbert. He defined a more general class of metrics on convex domains in Rn. Okay, so I was a little bit too long, but I really wanted to show you this lemma. And the proof, well, everything is on the archive, what I talked about, and this paper is posted in March of this year. Just let me add one more sentence. The method which is used in this proof, especially to get precise estimates, comes from just the idea, comes from this famous paper of Laszlo Lempert from 1981, in which he described geodesics of the Kobayashi metric in convex domains. So there is actually a very close relationship between this Beltrami metric and Poincare metric. I mean the Kobayashi metric or the Bergman metric. This metric is nothing else but the restriction to the real ball of either the Kobayashi metric or up to some multiplicative constant of the Bergman metric on the complex ball. So it's kind of the same formula as for the Kobayashi metric, except for in that case, x would be a complex variable and you would add a conjugate here on the second term. Otherwise, it's the same formula. Good. So let me thank you for your attention and stop here.
Thank you very much, Franz.
We have to thank you. Thanks a lot, Franz.
Are there questions? Comments?
May I ask a question? I'm Cinzia. Hi, Frank.
Hi, Cynthia. Nice to hear you or see you.
What happens if you know more? I mean, if you know that you have conformality not only in 1 point or maybe in 2 points, can you say more? Because in literature exists Schwarz and the Schwarz-Pick lemma also for many finite points, not only for 1 or 2 or.
Yeah, in which, what are these results exactly? In which?
Well, I can send you maybe some literature that I have, but the question is simply if you can say more, if you have more hypotheses. I mean, if you don't know simply the conformality in 1 point, but maybe in more points, in more finite points.
I don't know if it would change the statement because this statement, what would be then the statement? This is saying if you have conformality at 1 point, you have an estimate, and the equality holds only if you have this conformal affine disk, and in such case the equality holds at all points. So as soon as you have extremal value at 1 point, you have it everywhere.
Okay.
So I don't see where would 2 point condition come in. Because
this is the differential Schwarz-Pick. It exists a Schwarz-Pick not with only the map and not involving the differential. And in that
you
case,
mean for the distance function?
Exactly, for the distance. Exactly.
Yeah, I don't know.
And then if you know, if more than 2 points are involved, not only 2, you can say more.
So, why don't you send me this stuff? Because this is now just sort of the beginning. So of course, we get out of this, we also get theorems on distances. We know it's obvious, right? I mean, once you have such an estimate, you can, and you know that you're speaking of a metric, you can then have distances. And in fact, one thing we have done in this paper also is that we introduced a Kobayashi type metric on domains in Rn, but we use, instead of holomorphic disks, we use exactly the same construction as Kobayashi. But instead of holomorphic disks or chains of holomorphic disks, we use chains of conformal minimal disks in domains in Rn, in a given domain. And then, so you get an intrinsic pseudometric, which let me call minimal metric. And it turns out that, of course, then on the ball, it exactly equals to the Cayley-Klein metric. And I think that this is a kind of beginning of a new hyperbolicity theory, because, well, by now I've thought some more about this issue, and this Sibony metric can also be brought into the picture to give some lower estimates and to even to have some theorems about when is this pseudometric actually a metric? So when is the domain hyperbolic? Mm-hmm. So I'm hoping that this will develop. There is, of course, one key difference between the two theories. In the holomorphic case, you have a lot of holomorphic maps, and these metrics are distance decreasing for holomorphic maps. But in the case of conformal minimal disks, there are so many of them in Rn that the only transformations of coordinates which preserve the class of conformal minimal surfaces are the rigid maps, meaning orthogonal maps and translations, nothing else. So the mapping, sort of this mapping part of the theory cannot be very good. Even locally, you are not allowed to change coordinates. And that's why, for instance, the ball is a good model, but there are other models which should be studied. And I have a very precise idea which kind of models should be studied to get, better results.
Okay, but there is a recent paper of Abate on what I was trying to explain. I will send it to you.
Fine, just send it to me, yeah? Okay.
But this Schwarz-Pick lemma is really interesting. Thank you.
Okay. Thank you very much, Franz. So other questions? Okay, so
yes,
not, okay,
there is one quick question. Franz, this is Gautam.
Yes, hello, Gautam.
So this is about the pseudometric you were talking about again a couple of minutes ago.
Yeah.
Since we don't have the property of distance decrease under conformal maps in general, and hence under holomorphic maps, it doesn't kind of fit into the hierarchy of invariant metrics such that the Kobayashi distance always dominates and the Kara-Theodori distance is always the smallest. You were talking about using the Sibony metric, for instance, as a strategy for lower estimates on the pseudometric that you hinted at.
Yeah.
So did I miss something? Is it the case somehow that there is a comparison between say Kobayashi and Kara-Theodori appropriately interpreted? Because we saw this also when you talked about the Cayley-Klein distance. So is there some sort of appropriate interpretation? Maybe we are only looking at the Euclidean setting you embed into the diagonal and so on.
Yeah. You're finished with the question, right?
Mm-hmm.
Okay, so the thing is the following. You're entirely right. There are, as I said, there are not, besides rigid maps, you cannot use other maps. By the way, Kobayashi also has a paper where he studied some things of this kind. I think this was in '76, in the holomorphic case, but under affine changes. So he allowed affine changes in the projective spaces. But in this case, okay, so what is true? If you define this pseudometric the way I just told you, that you use Kobayashi's definition, but with conformal minimal disks. Then, of course, by the very definition, if you map any conformal surface, hyperbolic conformal surface, so one universally covered by the disk, into the domain, then, I mean, as a minimal surface, then, of course, the metric will decrease and the equality will be if and only if it's, and so forth, you understand.
Mm-hmm.
But now we don't have holomorphic functions, so there is no way to define an equivalent of a Carathéodory metric. We have no class of functions, but we have a class of plurisubharmonic functions, which I didn't talk about, but I have a full chapter in the book about them, and they're called minimally plurisubharmonic functions. They were actually discussed also in some 10 years ago or 15 in a string of papers by Harvey and Lawson. So let me tell you what is a minimally plurisubharmonic function. Okay, so you have a real valued C2 function. You look at its Hessian at any point, and you look at the eigenvalues of the Hessian, and you order them, say lambda 1, lambda 2, etc. So lambda 1 and lambda 2 are the smallest. Now you take the sum of lambda 1 plus lambda 2, the sum of the smallest two eigenvalues, and you ask that this sum is bigger or equal to 0. Okay, call this class of functions minimally plurisubharmonic. Instead of 2, you could also take any number of them, say p smallest eigenvalues, and you ask that the sum is bigger or equal to 0 at each point. But let me take 2. And then there is a theorem that this class of functions is precisely the class with the property that the restriction of such a function to any conformal minimal surface is a subharmonic function on the original Riemann surface. So this means that these functions play exactly the same role in this theory as the usual plurisubharmonic functions play in complex analysis.
I see.
And so the question now is, what does Sibony do? Sibony says, well, I can estimate Kobayashi metric from below by looking at functions which are not just plurisubharmonic, but okay, so he takes functions with values between 0 and 1, and the log of that function has to be plurisubharmonic. So those functions are called log plurisubharmonic. And then he looks at the maximal possible value of the Laplacian of such a function in a given direction. So somehow he estimates how big, if you're at a given point and you look at the space of all such admissible functions, and then you maximize the Levy form inside this class. And this is the definition of his metric. And this I can precisely do in this category because instead of just replace word by word and look at his proofs in some sense, and lots of things come out. And so in particular, I can show that, well, by using what I already have on the ball, I can show, and it's easy, that every strongly convex domain is hyperbolic, complete hyperbolic in the sense. The next question would be, is it Gromov hyperbolic, right?
Mm-hmm.
And then in this theory, there is a class of domains which are analogous to strongly pseudo-convex domains in CN. And namely, these are domains which have defining functions which are strongly minimally plurisubharmonic. This can be characterized in terms of boundary curvature of the boundary surface. So somehow they have positive mean curvature, right? These boundary surfaces. And my conjecture is that such are also complete. I mean, a bounded domain of this kind is complete hyperbolic in this new sense. But this I cannot prove. It's because somehow the proof of Sibony does not then carry over to this case. The problem is in many of these things, the problem is that there is such a huge amount of these minimal surfaces as compared to complex curves, you see. So complex analysis had become to appreciate is such a beautiful theory because it's you have maps, it's a category, right? But this theory is somewhat different. It's not. This is also the reason, by the way, why you cannot have a very simple proof of this kind of Schwarz lemma. It's because compositions of harmonic maps with almost anything will not be harmonic anymore.
Of course, yeah. Mhm.
So thank you very much. I think we are getting much over time. So really thank you very much.
Okay, sorry about being over time, and thank you.
It was very interesting and informative.
That's why we run the schools, so.